Okay. So this is what we hear very often. Okay. We are stuck. We need better lab data. Can you quickly do some experiments? Oh yeah. Funding? Oh no. We need to use it for other things. Sorry. So here it is. Historically, we had ground-based, experiments since we became Homo sapiens and beyond. And then somehow we looked into space, and then now we are sending spacecrafts into the space, and we get observations. And then I think one of the first space observations was probably Fraunhofer looking at moon and said, yeah, it looks like sun, because we had the ground data for sodium, and then it had the sodium lines in that. Maybe I'm wrong. Bottom line is, theoretical models use experimental data to interpret the observations. Okay, so these three are very important, and they have to work together. And I organized about 10 years ago the Science of Solar System ISS workshop along with Julie and Bob, and we try to actually bring these three together. Okay, and some of those things were successful, and we today also have to look into how we work together in order to bring these three elements together. Okay. Then, one of the important things that we have to keep in mind, incubation time for spacecrafts and things like that, even ground-based observations, if you want to build a 30-meter telescope, is 20 years. Sometimes it is the lifetime of an researcher starting very innocently. Theoretical models take also several decades to mature. Lab studies, I'm putting conservatively about 5 years. But there is also some kind of incubation time. You have to keep that in mind. If we want to have data, we need to really start looking at it right now, rather than when we have the spacecraft data and say, oh, we don't understand. And by the time we try to understand, it's gone. So this is actually relative size of availability of data and investment. We know that we invest really big because this is the one which actually shows us or gives us the visibility in the community.
So I gotta say, you gotta get rid of that ground part of your for the big thing. The ground is a tiny little thing about this big.
It's okay, Right? So do you want me to put ground into this?
I'm smaller than that.
Okay, I will ground you. So theoretical models have much more data, much more investment in that, because we have a lot of volume in this. But bottom line is, investment in lab data is not good. Okay, so we have to think about it. And finally, this is what I want you to actually take with you today, is based on thin, probably lab data, which you did not evaluate and you did not know the error limits. If we keep on building inverted pyramids on them, we are going to fail. Okay, so we need to keep in mind that whenever we build inverted pyramids, our foundation is really strong. Okay, and models, for example. So I will give you 2 or 3 examples of it. One of that is what Reggie really likes, sulfuric acid hydrates. Okay, and again, science cannot be because I find it believable, it must be true. Science should be an independent process of proven facts. So it is easy to think that sulfur reacts with water, making sulfuric acid hydrate. And this is the first paper where experimental work was done by Bob Carlson and Bob Johnson here and Anderson, and they showed that probably this should be most likely sulfuric acid hydrates. And in fact, they also took different grain sizes, but these grain sizes, I think, were some other sieves on which sulfuric acid hydrate was deposited. In any case, this is the first experiment. And I said that, is it really sulfur implantation into water ice experiment? And a lot of people said yes, in this group. I went and looked into it. It was not. It was H2S, SO2, and all those things, radiolysis of them in water. The only first sulfur implantation was done by Baragiola group, I think 2012, and 2013 is this one, where after heating to 190 Kelvin, they get in the mid-infrared the band of sulfuric acid hydrate. Okay, this is the one which was proven there. And if they don't do that at 80 Kelvin, there's a lot of gunk here, and that we don't know what it is. So, of course, who did this experiment here? Oh, this guy here. Oh, okay. Is it Reggie? Okay, Reggie. So he did the experiment with Mark, and exactly they showed that at 86 Kelvin, you have sulfuric acid hydrate, by the way, sulfuric acid in water ice, and then you make this hydrate here, I think mono or di or tri or tetra, it doesn't matter. If you irradiate it, the band is gone. And if you warm it up, again it comes back. So radiation plays a very important role. Okay? The bottom line is sulfuric acid hydrate may be there, perhaps very likely, I'm not denying it. But fact checking is not proven to be the bands that were there in 1 to 2.5 microns even today. And we don't know the radiation effects. Okay? This is the lesson number 1. Case study number 2 is about radiation, stopping range, how much it goes in. We discussed, Tom gave a very good talk, and he should pursue it further. And there may be differences, but we will reconcile it at one day, and then we get much more rigorous information out of it. But the bottom line is, the radiation yields, these are radiation yields, in other words, photons coming out. The photons come out as from the medium or get into the medium, the higher the electron energy. And these things will play a very important role based on how long things stay there without mixing, without transportation. And that's a very important thing we have to keep in mind. Second thing is, all the models that anyone did so far on Europa radiation are on liquid water. Data from the liquid water. Okay? That may be different from ice. It may have grain size effect, it may have other effects. So we have to, including salts or sulfuric hydrates and all those things, we are now coming to all those things. So this is case study number 2. We should be careful. We should try to be more, not doubting, but say that these are the limitations. These are the parameters we used in our models. And there may be some differences between what is there happening on Europa and what is that we have used as the initial parameters in our models. Third thing is O2. John Spencer gave a very nice talk about these two bands, and this is the first observation, and they're actually assigned as oxygen, but it is a minimum of O2 dimer is needed in order to induce these bands. Okay. So we did long ago experiments, and this is an emission actually, and we have this 0,0 band of 2 oxygen molecules and emission here. This was a thesis from my PhD student in Germany long ago, and this transition is from the ground state to the excited state of 2 oxygen molecules. Okay, and this is also nicely seen in the spacing of the vibrational states. Now, it is very well understood why this actually transition happens in O2 dimer. There is plenty of literature on that, and in fact, it seems this transition is also driven in the gas phase if there is enough O2 density. So we have to be careful where this absorption is coming from. One of the things that I think could be happening is that O2 may be made in the deeper, a few tens of centimeters or a few centimeters deeper, and then as it starts percolating, it forms bubbles, and then we have dimerization or even bigger clusters, and that could be the reason why we are getting it. So it could be a dynamic process here. I'm not saying that this is the truth, but it is one of the possibilities. Okay, so case number 3, they have done a very good job. We have very solid information, but still, up to date, we do not have understanding of this mechanism in the laboratory using water as the medium. Okay, good. So these are the three cases, and I have gone deep into the source of the data that is used. And it may be right, it may not be right, but we have to evaluate the data every time we do something. Otherwise, we will build the inverted pyramids on very big foundation. That's the message I wanted to give you through those things. Now, assessment. What do we know? By the way, the reason why I'm not talking real science is Vishal talked about it, and Brianna would be talking about it, so I decided that I will talk nonsense, okay? So, what is the non-ice component? We don't still know. According to Mike Brown, hydrated sulfuric acid is more or less positive, but rest is for grabs. And we don't know the radiation on this non-ice. Surface to interior material exchange, I have been talking about it again and again. This is one of the most important things we need to constrain. If we don't constrain, we are not constraining the whole processes, okay? And plumes may be different, they are active. Upwelling may be different, cryovolcanism may be different, but otherwise, if we don't have those things, how is the material exchange happening between the surface and interior? That's a very important thing. And how is the refreshing rate of the top, 1 to 2 meters? We don't know yet. So these are all the questions I have here. Amorphous versus crystalline ice composition on Europa's surface, leading hemisphere. This is something that we have to be very careful. The present estimates of 20 to 25% amorphous on the leading hemisphere does not correlate with the experimental knowledge we have. So we have to be careful about it. So, in order to understand, Europa's composition, which is a dynamic, exchange between exosphere to surface to the interior, there are two extremes. One is that they're completely, detached, and what is happening on the surface, take out these active things, but otherwise is not going in or not coming out. Other one is that we have very rapid exchange. In between these two, we need to really constrain what we are having there and how we can look into it. Molecules and materials, we have talked about it. These are all the things that would happen, as Reggie already talked about. And then sulfates and organics, what is happening to organics is very important to know for us. And then organisms to organics. That's a big step there. How those transitions are happening, what is the radiation dose, all these things are still up for grabs, okay? So we need to evaluate the source data and know where the limitations are. Partnership, we need to have partnerships among, communication, that's important. Simulate Europa's environment, laboratory data is not so much, and we need to start, getting funding and then probably collaborate so that we can reduce the, investments. Good. So we need we need actual input from you. Okay, this is the plugin that I wanted to actually do last time. You asked the young lady there. You asked the question that what are the possibilities to do lab experiments? Don't worry about the limitations of lab experiments. If you are a modeler, if you are an observer, if you think you want some lab data, go to one of these crazy people and ask them, we want this data, and then the dialogue starts. If you think that it may be too much for them, you keep that question to yourself, okay? Go to them and ask them the question. They may have some way of coming up with answers, okay? That's it. So today Daniel is here, Vishal is here, Brianna is here, and Jody is also here. This is a part of our group, and also Brianna's group actually here. Thank you very much.
Questions?
One slide.
Yeah, the laboratory data under simulated Europa environment is sparse. I agree. I mean, I agree with everything. I think you should add on there that the laboratory data needs to include measurements that will that the Europa clipper will be measuring so that we can compare the laboratory data to the spacecraft data?
So the one of the reasons why I completely avoided talking about any missions is that this meeting is more about science, and I think spacecrafts and the groups who are involved in this should very critically look into what data they have and what data they need, and I'm a part of it. So if I wear another hat, I completely agree with your statement. If I wear this hat, really, I completely agree with your statement.
I have no problem with those bands not being the sulfur things that you're. But what are they? What are the other possibilities? I've heard a couple times now that they might not be correct. That something.
I'm not doubting these two bands could be from sulfuric acid hydrates.
Well, you say, but you always qualified. So what are the suggestions? I mean,
I only said that lab data is not available under these wavelengths done with sulfur implantation to say that indeed the mechanism is what is happening, and so we see it in the lab.
So everything has to be reproduced in the lab. I mean. Because it's difficult, the penetration of the typical sulfur atoms into a very thin film.
They did
Again,
it.
I don't want to argue. I mean, if it's something else, it's something else. I'm just curious what your thoughts are.
I'm not denying. What I want to say is I don't know. I'm not denying. Okay, but Baragiola did it. They bombarded sulfur ions into water ice, but they were looked into real mid-infrared, not in the near-infrared. And if they were to look into near-infrared and find these bands, then the thing is solved. So I'm not doubting that.
No, it's fine to doubt. I mean, that's science, right? But it's also good to have another idea.
I think the lab experiments so far done were having sulfur there. One question I had is, when we take the sulfur or sulfates or SO2 or H2S, you don't only make H2SO4 X H2O. You make a lot of other molecules under radiolysis, and we have no idea about what all the other molecules are. I would say that we should probably do an experiment where we put sulfur ion into water ice and then look into mid and near infrared. That's as simple as my suggestion is. If I were to be given, let's say, if we were to write a proposal, and if I were to be given funding, that's what I would do. To do it in the near infrared, and mid infrared.
Quick questions.
So a quick one. It's a programmatic question. So that earlier slide you showed about, the lab being really small down there. What is, in your opinion, how big should that circle be?
As big as you can do the data for people who wanted to have the data.
I mean, that's really unconstrained, right? I mean, somebody can come to me and say, hey, get this data. I mean, how off do you think this is from a NASA's programmatic balance point of view?
So I would say that we have some systemic problems, but we can discuss about it later. But I would say that typically a lab needs 2 to 3 times more resources than a modeling group, okay? Because we need to maintain the instruments and all those things. And that's what you need to keep in mind when you're talking about investment. Either the investment should be done by the individual institutions, which they have to get the money from somewhere, or it should come from another pot.
Last question.
Okay, Murthy, I think something has been forgotten, and that's that the Clipper mission has 2 other instruments, and that's the mass specs and the SUDA instrument, and I see absolutely no mention of that. So I don't think that the finding out the composition is solely relies on the IR instrument, and those other instruments will also need similar efforts. And I would like to point that out.
Definitely. When I said the experiments, it's for everything. It's not like.
It seems to me that this is that mostly is IR that we are talking about.
I discussed about exchange between surface and exosphere. Okay, that we need to understand too.